Introduction to Quantum Mechanics. Introduction to quantum mechanics. Elementary idea only. Idea only. Okay. यह क्वांटम मैकेनिक्स हम जानते हैं कि एक्चुअली हम लोग जो मैकेनिक्स सॉरी एक्चुअली हमको क्वांटम मैकेनिक्स में देखना है कि जो व्हाट इज classical mechanics what was the need of developing quantum mechanics. Third, the basic equations of quantum mechanics Fourth, method of calculating energy of electron using quantum mechanics. And last, explanation of Heisenberg uncertainty principle. Heisenberg uncertainty principle by quantum mechanics. Yes. Now, actually, the discussion of all these points will take about 2 hours or more than that, 2 hours. Therefore, I have decided to divide this lecture into 2 parts, part 1 and part 2. From here to here, this is part 1, and from this point to this point, this is part 2. Part 1 and part 2. Now see, part 1, which is what is classical mechanics? Classical mechanics classical mechanics is the mechanics that starts from mechanics that start from Newtonian equation. Newtonian equations. In classical mechanics, we have two types of equation. Classical make two types of equations. That is separate equations. Separate equations for particle and wave. पार्टिकल के लिए जब हमको सपोज करो कि पार्टिकल का एनर्जी निकालना, पार्टिकल का काइनेटिक एनर्जी निकालना, तो हम यूज करते हैं हाफ mg स्क्वायर। जब इसका पोटेंशियल एनर्जी निकालना हो पार्टिकल का, हम यूज करते हैं mgh। जब इसका मोमेंटम निकालना हो तो हम यूज करते हैं इक्वेशन mv। जब हम फोर्स निकालना चाहें तो होगा P into F, force mf, sorry, m into F. The mass, m is the mass of the particle, v the velocity of the particle, then g the acceleration due to gravity, h is the height of the particle from ground. Again, mv already explained, and this f is the acceleration. So these are Newtonian equations, and these equations are used for particle. But for wave, there are separate equations for wave. There are two types of wave. One is electromagnetic wave. Electromagnetic wave. The energy of this wave is determined using Planck's constant E is equal to h nu, where h is Planck's constant and nu is the frequency of electromagnetic wave, that is frequency of radiation. First, you must know what is electromagnetic wave. Actually, electromagnetic wave is a wave that consists of both electric and magnetic field mutually perpendicular to each other and also perpendicular to the path of propagation. It's like this. Suppose this is the electric field, this is the magnetic field. They are mutually perpendicular to each other, and they are also perpendicular to path of its propagation. Suppose electromagnetic wave is moving in this direction, then these two forces are of magnetic field and electric field are also perpendicular on the path of its propagation. Okay. So light is electromagnetic wave. The energy can be determined by E is equal to h nu. Nu is the frequency, or this is h c by lambda, because frequency is the light, velocity of light divided by wavelength. And again, this is h c nu bar, where nu bar is the wave number. So nu, this is the frequency, and the unit of this is cycle per second, that is hertz. Cycle per second means how many cycles the wave is being formed per second. That is in 1 second, how many cycles are formed, how many waves are formed. This is frequency. Then see the velocity of light. This is light, the value of which is 3 into 10 to the power 8 meter per second. Lambda is the wavelength. The unit of this is meter or centimeter. Then mu bar is what? This is the wave number. And the unit of this is what? This is per meter or per second, per centimeter, sorry. That is how many waves are fitting into 1 centimeter length, or how many waves are fitting into 1 meter length. This is wave number. And this H is Planck's constant. You already knowing the value of Planck's constant. Planck's constant. This is 6.625 into 10 power minus 34 joule into second. So by means of this equation, you will calculate the energy of electromagnetic wave. Now, one point that is to be mentioned here is that the energy of wave is determined using frequency, wavelength, velocity, wave number. These are frequency, wavelength, wave number. These are the characteristics of a wave. So for determining the energy, we use characteristic of the wave. Whereas for particle, we use mass. Mass is the characteristic of a particle. Okay, so this is the difference. We are not, mass can't be used here because mass is not the characteristic of the wave. So this is your wave. This is the equation for wave. Now there is another wave, and that wave is what? This is simple harmonic wave. This is simple harmonic wave. Simple harmonic wave. इस वेव को समझने के लिए आप HF मॉलिक्यूल कंसिडर करो. Consider HF molecule. These hydrogen and fluorine atoms are joined by means of covalent bond. This is fluorine atom, and this is your hydrogen atom. Hydrogen is smaller in size as compared to fluorine, and this is the nucleus of fluorine. This is the nucleus of hydrogen, and the internuclear separation, that is the distance between the nuclei of these two bonded atoms, is the bond length of the molecule. Bond length is the internuclear separation. This distance is the bond length. Now, in a molecule, two types of forces are acting. The positively charged nucleus of one atom is repelling the positively charged nucleus of another atom. The positively charged nucleus of one atom is repelling the positively charged nucleus of another atom. Also, the negatively charged electron cloud of one atom is repelling the negatively charged electron cloud of the another atom. And as a result of this repulsive force, what will happen? This bond length will increase. That is, assuming that the position of fluorine is fixed, the hydrogen atom will go apart from the fluorine atom. The distance, the bond length will increase. And another force that also exists is the attractive force. The attractive force is the electrostatic attraction, is the electrical attraction between positively charged nucleus of one atom and negatively charged electron cloud of another atom. That is positively charged nucleus of fluorine atom is attracting the negatively charged electron cloud of hydrogen atom, and positively charged nucleus of hydrogen atom is attracting the negatively charged electron of fluorine atom. Now, attractive force, and as a result of this attractive force, what will happen? The atom and fluorine atom will come closer. So this means the bond length in this case will decrease. In the case of repulsion, the bond length will increase. In the case of attraction, the bond length will decrease. So actually, a covalent bond is behaving as though it is a spring. It is like a spring. It is a spring. Now, attractive force is long range force. Long range force. And repulsive force is short range force. What does it mean? This means when hydrogen and fluorine atoms remain far apart from one another, when the separation between them remain long, then it is attractive force that dominates over the repulsive force. That is, attractive force is stronger than the repulsive force. And as a result of this, what will happen? The internuclear separation will decrease. These two atoms will come closer to one another. If you suppose that the position of fluorine is fixed, then this hydrogen atom will come nearer to this fluorine atom. And repulsive force is short range force means when the distance between these two atoms, bonding atoms, remain small, short, then it is the repulsive force that dominates over the attractive force. That is, repulsive force is greater than the attractive force. Then what will happen? The repulsive force is greater. So this hydrogen atom, suppose which has come here due to attraction, will now be repelled back, and this will move away from this. Suppose it has come now here. This. So this is the position of hydrogen. This is the position of hydrogen in the equilibrium condition. That is bond length in the equilibrium, is the bond length in the nuclear separation in the equilibrium position. Equilibrium means when attractive force and repulsive force are equal. Then this separation is known as bond length. And due to repulsion, the hydrogen atom is coming here. This is displacement. And when it comes here, then the attractive force, which is long range force, because the distance has increased, so the attractive force becomes stronger than the repulsive force. And so again, this hydrogen atom will start coming closer to the fluorine atom. So assuming that fluorine atom is constant, the hydrogen atom is executing simple harmonic motion like this. This kind of vibration is called simple harmonic vibration, like this. Now, this is called displacement. This is displacement in the forward direction. This is displacement in the backward direction. Here, two types of where the force that is acting. One force that is important force that is acting is restoring force. There is a restoring force. Restoring force F. This restoring force is proportional to minus Kf. Minus Kx. Minus Kx. This x is the displacement. this x, the distance from the equilibrium position. Suppose this particle comes here, then this is the equilibrium position, and this is the displacement. This is the value of x. Now, and k is a constant. This is called force constant. Force constant. This measures what? Measures the stiffness of the bond. Stiffness of the bond. If the bond is stiff, that is bond is hard, the bond is strong, then force constant K will be high. So therefore, for single bond, force constant will be less. For double bond, the force constant will have higher value, and for triple bond, the force constant will be even more higher. Okay. Now we see that since K is a constant, so we can say that force is proportional to minus x. That is, restoring force is directly proportional to displacement. And this sign negative indicates that the restoring force is acting in the direction opposite to the displacement. That is, if the hydrogen atom is going this side, the restoring force will act in the opposite direction, will tends to pull the hydrogen atom in the backward direction due to your attraction between the two. And now, when this when this hydrogen atom comes here and its motion ceases to exist, then its kinetic energy will be zero. Here, kinetic energy will be zero. And this is the maximum what? Maximum displacement. This maximum displacement is known as amplitude. This is amplitude. This amplitude is A. Amplitude is A. So here potential energy is half K square at maximum. Yes. At maximum displacement, when displacement is equal to amplitude, at this point, the kinetic energy is zero of the system is zero, and potential energy half K squared. That is, you are using amplitude in calculating the energy. And at this position, which is the equilibrium position, at equilibrium position, when there is no displacement, at this point, the potential energy is zero because no any force is acting. The attractive force and the repulsive force both are equal at this point. So no external force is working. Therefore, potential energy will be zero. Here, potential energy will be zero, and kinetic energy will be half mv squared. So here at the equilibrium position, kinetic energy is half mv squared, the potential energy is zero, and at maximum displacement, potential energy is half k squared, and kinetic energy is zero. And in between these two, the energy, total energy, is partly as kinetic energy and partly as potential energy. So energy is equal to half mv squared, half mv squared. This is kinetic energy plus half kx squared. where x is the displacement. This is for the situation 0 is less than x is less than a. Then energy will be partly as kinetic energy, partly as potential energy. This means as this hydrogen atom moves away from this chlorine atom, the kinetic energy is converted into potential energy. And here, total energy appears as potential energy. And when this hydrogen atom moves in this direction, then potential energy goes on decreasing. That is, potential energy goes on converting into the kinetic energy. And here, the potential energy is completely zero, and kinetic energy, total energy is kinetic energy. So, in between these two, that is, for any displacement, x is the displacement, x is the displacement. For any displacement x, the energy is partly as kinetic, energy is partly as potential energy. So for a simple harmonic wave, the energy is calculated during this equation. Here we are using amplitude. Amplitude is the property of what? Amplitude is the property of wave. It is a characteristic of wave. So again, we are using the wave characteristic to calculate the energy of wave. So in classical mechanics, we have different separate equations for particle and wave. Now, let us see why actually Niels Bohr, who gave atomic structure, the theory of atom, he used classical mechanics for deriving the energy of electron because he considered electron purely as a particle. He considered electron purely as a particle. And on the basis of his theory, he was able to explain the atomic spectra of elements. In the atomic spectra of elements, lines appear. These lines in this way, lines appear. And he was able to explain the origin of each and every line in the spectrum. And therefore, Bohr's theory was very much accepted. Because in the line spectra, there was gap between two lines. There was gap between two lines. Therefore, both thought that the electronic orbits must not be continuous. It must be discrete. So he gave this kind of structure, that this is the nucleus, this is one orbit, one electronic cell, this is another electronic cell, this is third electronic cells. And these are the electronic cells in which electrons can revolve. Electrons can't revolve in between these two cells. Electron can't revolve in between these two cells. So the electronic cells are discrete as considered by Bohr. And Bohr also introduced quantization in the angular momentum of electron, and he said that only those orbits will be stable, or electrons can revolve only in those electronic cells orbits in which the angular momentum of electron is n into h by 2 pi, n into h by 2 pi, where n is equal to 1, 2, 3, up to infinity. This is the angular momentum of electron. So angular momentum of electron is either h by 2 pi or an integral multiple of h by 2 pi. And here n is 1, here n is 2, here n is 3. Here the angular momentum is h by 2 pi. Here the angular momentum is 2 into h by 2 pi. Here the angular momentum is 3 into h by 2 pi. Now here there is a gap between two orbits. and energy depends upon orbit. And the energy of this will be different from this, will be different from this. So in between two energy level, there is a difference in energy. And on this basis, we are able to explain why there is a gap here. This gap is here in the line spectrum. The Bohr theory was accepted. In the 1930, this Niels Bohr theory was accepted in the year 1930. After that, when science developed and a spectroscopy of high resolving power was used to determine the atomic spectra. That is, when the prism, resolving power of the prism was increased, and then a spectrum was taken, it was found that each line in the spectrum, this line, this appears to be single line here. But actually, this line is not single. This is group of so many fine lines like this. This is group of so many fine lines. Why these fine lines are there in every line? What is the origin of these fine lines? The Bohr was not able to explain. The Bohr's theory did not explain this point. So that was the first failure of Bohr's theory of atom. The second point was Bohr's theory was able to explain this for atom or ion containing only one electron. That is for hydrogen atom, for helium plus ion, for lithium 2 plus ion. This system contains one and only one electron. So he was able to explain the atomic spectra of atom or ion containing one and only one electron. One and only one electron. It could not explain the atomic spectra of atoms or molecule or atoms or ion containing two or more than two electrons. For example, you can take lithium, helium. It takes there are two electrons. Here there are three electrons. And the atomic spectra of helium, lithium, beryllium, boron, carbon were very complicated. The number of lines were very large, and Bohr's theory was not able to explain the existence of those lines in the spectra. So that was another failure of Bohr's theory. The third failure started with the development of Heisenberg uncertainty. Heisenberg uncertainty scientific principle. This Heisenberg in the year 1927 perceived the idea that it is not possible to determine both the position and momentum of a microscopic particle like electron, proton, neutron, atom, molecule, ion. For such a microscopic particle, minute particle, it is not possible to determine both the position and momentum simultaneously with accuracy. Meaning thereby that if position is determined accurately, then momentum can't be determined. Momentum can't be determined accurately. If it is determined accurately, it can't be determined accurately. Or if momentum is determined accurately, position can't be determined accurately. If the position is 100% correct, the momentum will be 100% incorrect. If the momentum is 100% correct, the position will be 100% incorrect. 100% incorrect means, suppose we say that an electron has this much momentum. Where is the location of electron? Then what you will say? You will say that electron will be somewhere in this universe. The electron will be somewhere in this universe. That is, the position will be completely uncertain. Mathematically, Heisenberg's principle is written in this way: delta x into delta p is greater than or equal to h by m 2 pi, 4 pi. Now this delta x is the uncertainty or error in the determination of position, and delta p, which is equal to m into delta v. This is the uncertainty, that is error in the determination of momentum. Now, from this equation, it is quite obvious that when delta x will be 0, delta x 0 means there is no error, there is no uncertainty, there is no error in the measurement of position. That is, position is 100% accurate. And then delta p will be how much? This delta p will be this divided by 0. Anything divided by 0 will be infinity. So we see that when position is 100% accurate, then momentum is infinitely incorrect. The error in the momentum is infinite. Similarly, when delta p is 0, then delta x will be infinity. That is, when the momentum is exactly determined, then the determined position will be 100% incorrect. But are not possible to determine the position. Now, examining on this principle, the Bohr's theory of atom will be found to highlight this principle. One thing that let me explain why Heisenberg perceived this idea. What was the reason? Just then I will again come in. Heisenberg perceived this idea thinking that there is one important theory of physics. And this theory is, if you want to, suppose this is x-axis, and here x is the displacement. Here x is, suppose, 5 centimeter from the origin, from this point. Okay, from this is the origin. Here x is 0. Suppose there is a particle here. What is the position of the particle here? The position is particle is at 5 centimeter from the origin. Now, if you try to locate the position of the particle using photon of this wavelength, because we have to use photon to see any object. We have to use light. You need light to see any object. In darkness, you can't see anything. Actually, when photon falls on the object, it is reflected back and falls on our retina, and we have the experience of vision. We are able to see the object. So, therefore, light is a must. Now, suppose we have to locate the position of this particle, and you are using photon of this wavelength. What will happen? This photon, when a strike at this particle, the size of this particle will be large. It will become of the dimension of the wavelength. This particle is small of this size, but you will see particle of this size. Now, you have to report what is the position of the particle along the x-axis. Now, suppose here it is 3 centimeter and here it is 7 centimeter. Then you will have to say that the position of the particle is 5 plus minus 2 centimeter. This plus minus 2, this is the error in determination of the position, because particle is at 5 centimeter. But the photon you have used has enlarged that particle, and so there has been error in the location of the particle. Therefore, what should be the wavelength so that the position of the particle can be exactly determined? The wavelength must be of the same dimension. The wavelength must be of the same order as the diameter of the object, so that if the wavelength is this much, then it will be enlarged by the same. There will be no enlargement. The object will be of same size. The size will remain constant, and then exactly you can determine the distance. So one point that you must remember is that in order to locate the position of any particle exactly, you will have to what? You will have to interact the object with photon whose wavelength is of the same order as that of the dimension of the object. Okay? So see, object and wavelength of photon. Wavelength of photon to be used. Now, if the object is this size, you can use photon of this wavelength, this diameter, this is equal. If the object is small, you have to use wavelength of a small wavelength. If the object is even smaller, we have to use the photon of even a smaller wavelength. Suppose electron, let us consider electron. An electron is a microparticle. And then what will happen? To see an electron using photon, the wavelength of photon should be how much? Should also be very, very small. Should also be very, very small. Now, here again, there is one theory that you must know. This is Einstein's theory. Yeah, Einstein's equation. Actually, light was supposed to be wave. The properties of light, such as reflection, interference, diffraction, all these properties can be proved if light is supposed to be wave. These are the properties of wave. But in photoelectric effect, Einstein, the result of photoelectric effect means when on any metal light falls, when light falls on any metal, the electrons are ejected, the electrons are emitted from the metal. And for this, the frequency of wavelength, frequency of photon must be some definite value, not less than that value. It may be that value or more than that value. So there is a threshold frequency for the emission of electron from the surface of metal. And it is found that as soon as we just allow to fall light of frequency equal or greater than threshold frequency of metal, electron begins to be emitted from the surface. Electrons begin to be ejected from the surface. Now, how many electrons will be emitted? That depends upon the intensity. Now, it was found that as photon falls on the metal, the electrons are emitted then and there. Simultaneously, light falls and emission begins. These facts tested that the entire energy is taken, the energy needed to remove electron from an atom at the surface is taken by the metal in one installment. It is not absorbed continuously, rather it is absorbed in some definite amount. And therefore, this was, Einstein thought that the light has particle nature. The particle of energy that is taken by the metal, entire particle is taken in one go. Okay, so particle nature was established. Photoelectric effect. So light has now dual nature. Light has wave nature, and light has particle nature. Wave nature was based on the properties of light such as reflection, interference, reflection, and the particle nature is based on the photoelectric effect or Compton effect. Okay. Now, Einstein gave an equation relating the wavelength of light wave and the momentum of light as a particle. Momentum is mc, mass into velocity of light. Mc, this is the momentum of light particle, and this is the wavelength of light. So Einstein suggested that these are interrelated as lambda is equal to h by mc. That is, the light whose wavelength is high, the momentum will be less. And the light whose wavelength is low, is small, the momentum will be very high. So now, let's see. Now, since in order to locate the Poisson of electron, we are using wavelength of microscopic size. So what will happen? The momentum of this will be how much? Since wavelength is very small, so momentum will be very high. So photon of very high momentum can only be used to locate the Poisson of electron. And when such a high energetic photon or high momentum photon will strike this electron, what will happen? There will be momentum transfer. The momentum of photon will be transferred to this electron, and the electron will be, the velocity of electron will increase. So, although you have located the Poisson of electron, you can't say anything about the velocity of electron because velocity of electron had changed. due to impact with the photon and transfer of momentum of photon to the momentum of particle. So we see that you can determine the position of an electron only by disturbing the velocity of electron. Without disturbing the velocity of electron, you can't determine what? You can't determine the energy of electron, sorry, the position of electron. That is, during position determination, the velocity of electron is disturbed. Similarly, it can be proved that while determining the momentum of electron, that is determining the velocity of electron, you will have to change its position. You will have to change its position. So we see that out of position and momentum, both can't be determined simultaneously because one is determined by disturbing another. And this applies for a microscopic particle like electron, proton, neutron, atom, molecule, and etc. So now let us come. Now Heisenberg uncertainty. Now where they say, okay, momentum. So just now this is Heisenberg uncertainty. So sorry. Now actually when the board theory was examined on the Heisenberg uncertainty principle, it was found that this model violates Heisenberg uncertainty principle because Bohr was able to determine the position of electron in any atom. That is, in hydrogen atom in the first orbit, electron is at this distance, 0.529 angstrom distance. The energy of electron here is minus 13.6 electron volt. Similarly, velocity is also known. Now that is against Heisenberg uncertainty principle. It violates Heisenberg uncertainty principle, which is the law of nature. So that was a great blunder on the part of Niels Bohr while proposing his theory. It was understood later on that it violates Heisenberg uncertainty principle. Again, it was found that when atomic spectra are taken in magnetic field or electric field, the spectral line is split into components, into several lines. The splitting of spectral line in magnetic field is known as Zeeman effect, and the splitting of line in what? In the electric field is known as a Stark effect. Zeeman effect, Zeeman effect, and Stark effect. Zeeman effect is what? This is splitting of lines, spectral lines in the magnetic field, and the Stark effect is splitting of lines in the electric field. And Bohr's theory was not able to explain why there is a Zeeman effect or Stark effect. Now, in the year 1924, de Broglie, a French scientist. He was not scientist, he was a defense personnel actually. Although he was in the defense service, he was very interested in understanding the development in the field of science. So when Niels Bohr's theory came into being and everybody was praising Bohr's theory, that Bohr was able to explain the line of spectra of atoms, then he became interested that what is Bohr's theory of atom? And when he understood what is Bohr's theory of atom, then one thing was always haunting his mind, and that was that there is a gap between two discrete two orbits. An electron can revolve here, the electron can revolve here, but it can't revolve in between these two. Why? You probably say why? Why it can't go? What is the problem if electron will move here? Now nobody can challenge Bohr's theory because Bohr's theory was able to explain the spectra of atoms containing one electron. So the validity of Bohr's theory was already established. Here, why don't the electron revolve here? That haunted the mind of de Broglie. And he conceived the idea that this is possible only when it is assumed that electron has wave nature. Electron, which is a particle, which is a material particle, material, particle of matter, because it has mass. De Broglie suggested that it is possible only when electron has wave nature. Only when electron has wave nature. But how? He suggested that this orbit, and he also said that one should not problem in accepting that particle can behave as a wave also. Because Einstein had already proved that light, which was wave, is also behaving as a particle. So when a wave can behave as a particle, why not particle can also behave as a wave? So one has to accept that particle can behave as a wave, that electron can behave as a wave. Now, suppose this is the orbit. And suppose the circumference of this orbit is, 10 centimeter. And the electron wave, this is one wave, one cycle. Suppose the wavelength of electron wave is 2 centimeter. Then what will happen? How many wavelengths will fit into this circumference? 5 wavelengths will fit. This is one wavelength. This is second wavelength. This is third wavelength. This is fourth. And this is fifth wavelength. And when fifth wavelength will complete, that is fifth cycle will complete, then the wave here at this point will move in the upward direction. And the previous wave, the first wave that has started from this point, is also making displacement in the upward direction. This means the previous wave and the wave following it, they are meeting the same phase. They are meeting the same phase. That is, the crest of one wave is falling over the crest of another wave, and as a result of this, there will addition of amplitude. The amplitude will increase, and such an orbit will be a stable orbit. But suppose in this circumference, in this orbit, let us suppose, which is 10 centimeter in circumference, we have this is one wavelength, third wavelength, this is third, and this is fourth wavelength, and this is your, yes, this is again, one. Suppose we have a orbit whose circumference is 10 centimeter and wavelength of the wave, electron wave, is 2 centimeter. Then Suppose the wavelength is, the wavelength is, this is just 12 centimeter, and the wavelength of the wave is 3 centimeter. Then how many waves will fit into this? 4 waves. And if a wavelength is, suppose it is 3.5 centimeter, then how many waves will fit into this? The waves will be fitting into this will be, if you multiply this by 4, no, 3 and slightly more than 3. So this kind of this, one wavelength, this is second wavelength, this is third wavelength, and this. Here, at this point, where the first wave has started, the electron wave has started to vibrate, and the proceeding wave, this is coming in the downward direction. And the first wave was, at this point, was going in the upward direction, and this is coming in the downward direction. This means one wave is opposing the another wave. That is, the crest of one wave is falling over the trough of another wave. And what will happen? As a result of what will happen? One wave will cancel another wave. One wave will cancel another wave. And then the orbit will vanish. So, de Broglie suggested that electron has wave nature, and only those orbits are stable in which the angular momentum of electron is integral multiple of wavelength. That is, lambda is the wavelength, and this is 2 pi. Sorry, this is the circumference is 2 pi r. 2 pi r should be n lambda, where n is 1, 2, 3, and up to this infinity. And if this is the condition of a stable orbit, and if the value of lambda, again, de Broglie also made one hypothesis that just as for light, which is both as a wave and particle, this equation applies, lambda is h by mc, that is particle nature of light and wave nature of light, they are interrelated with one another according to this equation. De Broglie, in analogy with this equation, suggested that the same equation also applies for the material particle, which behaves both as a particle and as a wave. That is, for the electron, same kind of equation will be applicable. That is, wavelength of electron wave is equal to h by momentum of electron. If the electron of mass m is moving with v velocity, then the momentum will be mv, and then lambda is h by mv, and lambda is h by mv. So this equation is known as de Broglie's equation, and if this equation is put into this equation, you will get 2 pi r. This is n h by mv. And by rearranging, you will get that mvr, mv into r. This is n into h by 2 pi. Now, where n is what? N is 1, 2, 3, up to infinity. So that's it. The same equation was given by Niels Bohr, that the angular momentum of electron is quantized. Angular momentum can have only some certain values. It must be either h by 2 pi or an integral multiple of h by 2 pi. And same formula, same condition was derived by de Broglie using wave nature of electron. And actually, de Broglie was writing a PhD thesis in the year 1924. And when he has written all these things in his PhD thesis, PhD thesis, PhD thesis. Okay. The examiner, while examining his thesis, was very furious with de Broglie. He was annoyed that this research fellow is talking only hypothesis in the thesis. All are hypothetical facts. He was so much annoyed that in his feedback he wrote to the university that Mr. de Broglie should be awarded PhD degree, with condition that you will have to remove all pages. You will have to remove all pages containing these hypothetical facts from the thesis. Only then he should be given PhD degree, otherwise not. So for getting PhD degree, de Broglie was very sad, but he had to take PhD degree. So he removed all such pages from his thesis and then again submitted the thesis. Again, examiner just passed through, yes, okay, now it is okay. He should be given PhD degree. Okay. So now what happens here? The pages on which his PhD degree was at stake, he was not able to get PhD degree. On the same page, he will be on the same pages, you will get Nobel Prize. Actually, in the year 1927, Davison and German, two American scientists, were carrying out an experiment. The experiment was like this. This is a nickel plate. This is polycrystalline, not crystalline, polycrystalline. And he was striking a beam of electron. This is beam of electron. This beam of electron carries negative charge. The beam of electron. Actually, before striking a beam of electron with a nickel plate, he passed this electron beam through an electric field of 50-volt potential difference. He passed this electron beam in an electric field of potential difference equal to 50 volt. What will happen? The electric field will accelerate electron. The velocity of electron will increase. So electron was first accelerated, and then it was made to fall on a strike. Then it was made to strike a nickel plate. Actually, Davison and German, they were interested to study the reflection of electron beam. They were interested to study reflection of electron beam. Okay. So, in order to determine that at what angle the electron beam had reflected, he used a galvanometer. He just rotated galvanometer from this point to this point to see where deflection takes place. The point where deflection will occur, that is the point where reflected electron beam is present. So when he carried out this experiment, performed this experiment, they were amazed to see the result. The result was that the electron was here, the electron was here, the electron was here, the electron was here, the electron was here. This kind of result was. That was a wonderful result, very amazing result. That it is not an example of reflection. It is an example of diffraction. The electron beam is getting diffracted. This means in between these two, there is no electron beam. That is, electron has wave nature. And one electron waves are destroying electron waves due to destructive interference. That is, crest falls on the trough. Therefore, here there is a blank, there is no wave. But here there is a wave. There has been constructive interference. Here there has been constructive interference. But in between these two, there has been destructive interference. So actually this phenomenon is called diffraction phenomenon. And diffraction is a property of what? This is a property of wave. So Davison and Janva reported that during this experiment, when they were carrying out the experiment to study the reflection of electron beam, there has been diffraction of electron beam, indicating that electron is a wave. Okay, this experiment was supposed to be the most luckiest experiment in the scientific world. Luckiest in the sense that he was studying the reflection of electron beam and got diffraction result. That was a great wonder. And second point was that for the diffraction of wave, a grating is needed. Grating is such a substance with which wave interacts, only then diffraction will occur. Only when diffraction will occur. And here also there is a condition that the sharpness of the diffraction grating must be of the same order as the wavelength of the electron to be diffracted. That is, if the electron wave has wavelength 10 to the power minus 8 centimeters of whole, and it is very small, then then the diffraction grating should be as sharp as this. As sharp. Actually for electron wave, crystal is used as a grating. In crystal, the interplanar distance is of the same order. And therefore, interplanar distance acts as a grating for the electron wave, for X-rays and electron waves. So, why it is the luckiest experiment? Luckiest experiment in the sense that actually it is a wave, okay, but this nickel plate is acting as a grating, because after striking this, diffraction takes place. Why it acts as a grating? It is a polycrystalline, and for the electron wave, the grating is crystal. It should be crystalline, but it is polycrystalline. Actually, they were most fortunate. They were very lucky. Since the electron beam was accelerated, it has very high kinetic energy. So no sooner it made impact on the nickel plate, the kinetic energy of electron beam was converted into some kinetic energy, was converted into heat energy, and therefore there was sudden rise in temperature of the nickel plate. And due to this rise in temperature, the structure of nickel plate changed from polycrystalline to crystalline. That is, Davison and Janwar has used polycrystalline nickel, But due to rise in temperature, it became crystalline at high temperature. And high temperature was achieved due to conversion of kinetic energy into heat energy. And when it became crystalline, then it started behaving as a grating and electron wave was diffracted. Now, but Davison and Dunbar work was not easily accepted in the scientific world. There were so many queries, there had so many doubts about this experiment. Therefore, G.P. Thomson, who was son of what? Thomson, son of J.P. Thomson, son of J.P. Thomson, you must have J.P. Thomson. J.P. Thomson is what? He was a great scientist. He determined E by M ratio of electron, and he discovered the electron. Electron is present in every matter. And J.P. Thomson was son of J.J. Thomson, not J.P., J.J. Thomson. J.J. Thomson. J.J. Thomson has given his lab to his son J.P. Thomson. His lab was very sophisticated. And in that sophisticated lab, J.P. Thomson carried out the experiment on the diffraction of electron. And he was able to see that electron beams are really diffracted. Electron beams are really diffracted. And then the wave nature of electron was established. Wave nature of electron was established. Okay. J.P. Now, Davison and Dunbar were awarded with Nobel Prize. Later, J.P. Thomson was also awarded Nobel Prize. And then, de Broglie also got Nobel Prize because they found electron is a wave by experiment. And de Broglie, without carrying out any experiment, he perceived the idea that electron has wave nature, and on the basis of wave nature of electron, he was able to derive the quantization in the angular momentum of electron. So that was the essence of the theory of de Broglie, the concept of de Broglie. He got Nobel Prize. So this is very surprising that the Piaget, which obstructed de Broglie to get PhD degree, on the same Piaget, he was able to get Nobel Prize. Okay, now next point is electron has wave nature. Now the question was how to calculate energy of electron. You can't use classical mechanics because in classical mechanics there are separate equations for particle and wave. In classical mechanics there is no equation for any system possessing both particle and wave nature. So there was no any equation for calculating energy of electron. Therefore, there was need to develop a new mechanics which can be used to find out energy of a system containing both particle and wave nature. That is electron. We are talking about electron. This system is electron. And that was done by Schrödinger. Schrödinger derived an equation. He just took classical wave equation, and in the classical wave equation, he put what? He put a de Broglie's equation. And doing this, he got an equation. And that very equation, there was wave nature of electron present and also particle nature present. And that equation was used to determine the energy of electron. So quantum mechanics started from this. Quantum mechanics started from Schrödinger wave equation, and need was because of the wave nature of electron on which classical mechanics can't be applied. So this is the first part of our lecture, and second part will start after some time. Okay, this is all about the first part. If you have any query, you are free to ask me. I will try my level best to answer your query. Okay.